Well, welcome everyone. I'm Art Benjamin, and on behalf of the AMS, American Mathematical Society, it's great to have you all here. In the late 1980s, the American Mathematical Society instituted a series of lectures aimed at talented high school math students. In 1993, the series was dedicated to Professor Arnold E. Ross of Ohio State University for his many contributions to the development of mathematical talent. For 44 years, from 1957 to 2000, Dr. Ross ran a summer program for gifted high school students, giving the number theory lecture every morning. In keeping with this prestigious tradition, the AMS is proud to present the annual Arnold Ross Lecture for talented high school math students. These lectures are sustained in part by an endowment established by the late Professor Paul Sally of the University of Chicago. Well, it's wonderful to be here at Proof School here in San Francisco. It's a wonderful school, grades 6 through 12, for students who love math. And if you love math, well, you're in for a real treat today. Francis Su is a phenomenal speaker. He's a winner of the HAMO Prize, which is the National Collegiate Teaching Award from the Mathematical Association of America, the MAA, and was the first recipient of the Alder Prize, recognizing an outstanding new professor. He's received numerous awards for his writing, including the Euler Book Prize for his Mathematics of Human Flourishing, a bestseller. His page, Math Fun Facts, which you should all go to, is visited by more than 1 million people each year. And a number of years ago, he had a real analysis course recorded, a collegiate class on real analysis, and it's been viewed nearly 2 million times. He's a fellow of the American Mathematical Society. He's has been vice president of the AMS and the MAA, and in fact, he's a past president of the Mathematical Association of America. For the last 30 years, he's been a professor at Harvey Mudd College, where he serves as the Benediktsson-Karwa Professor of Mathematics. He's mentored over 60 research students, but best of all, he's one of my dearest friends. So here to present Randomness, Geometry, and Fairness, please big a great Proof School welcome for Francis Su.
Thank you. Thanks so much. It's really a pleasure to be here at Proof School and to represent the Arnold Ross Lectures. I was a high school student many years ago now, but I didn't have opportunities like the Arnold Ross program or Proof School. I really wish back then that I did. And so it's really nice to be part of a program that encourages high school students to learn more about mathematics and get excited about it. And I'm also pleased that this lecture is being live streamed to people who over Zoom, and wonderful the technology can make that possible so that people like me in rural parts of the country without opportunities might have a chance to see some cool math. So are you all ready for this? Yeah. Yes. Okay. Awesome. Great. So I'm going to talk today about three things that don't seem like they're necessarily going to be related: randomness, geometry, and privacy. And I wanted to say that it's also an opportunity to, let's see, how do I, hang on, my Zoom. I need to advance my slide. Oh, I guess I just pressed the screen for that. Awesome. Should know how to do this. Okay, great. So this is a story about mathematics, but it's also a story about people, also a story about how mathematics is often done. I spent a research leave from my home institution at the University of Sydney last year, 2024, at the Sydney Math Research Institute, which is down in Australia. As it happened, my office at the Institute was right next door to Salil Vadan, who actually 30 years ago was a student of mine. So I was an undergraduate I was a grad student at Harvard. Salil was an undergrad. I taught him in a class. And so I get to Sydney and I'm like, whoa, Salil. And it's pretty amazing. He's now a professor of computer science, and he was there to work with Clement Canon, who is also at the University of Sydney. And they are both experts in this area of computer science known as differential privacy. How many people here have heard of differential privacy? Okay, so it's a relatively new area of CS, and I didn't know anything about that. My area of mathematics is actually more along the lines of geometric and topological combinatorics. I study things that are combinatorial or geometric in nature often. And so I thought, oh, okay, well, it'd be interesting to find out what Salil does. And so I went to one of his talks on differential privacy. He came to one of my talks on Sperner's lemma. And afterwards, we started chatting because he said, hey, one of the problems I'm working on right now, some of the things you know about on Sperner's lemma might be able to help us. And so we started chatting. And so this was a serendipitous connection. Like it wouldn't have happened if we weren't actually in the same place at the same time. And so we started chatting about it and realized that indeed Sperner's lemma does relate to this problem. And so we started chatting. And so part of what I want to say here is that some of the things that happen in mathematics are more about connections and people coming together. So here's what I want to do. So the outline of my talk is I want to unpack the three things that are in the title. I want to tell you what differential privacy is. I want to tell you about this concept that we defined called randomness complexity. And then I want to tell you where geometry enters into the puzzle. I'm going to try to keep it mostly non-technical and intuitive. And that partly reflects the idea that, in a math talk, you really don't have the mental space to actually follow lots of technical details, right? And part of what you want from a talk is just to get the general strategies, some of the big ideas that are prominent in what the speaker is talking about. Okay, so that's the plan. And I also want to, along the way, talk about what math is and also how it sometimes happens, right? Like the math being the process of being able to make careful definitions so that you can talk about things and two people can actually get somewhere because they both are talking about the same thing. But it's also about making use of properties, right? Like you could define something really carefully, but in practice, you might only ever refer to the properties, right? Like, we could define a real number really carefully, right? But when it comes down to it, it satisfies certain laws like the distributive property or the commutative property, things like that, right? So you'll see that happening, that kind of thing happening in this talk. And the idea that math is often about looking at problems from many different perspectives, right? Like it was helpful that we had geometric perspectives as well as perspectives from computer science. Math is often about higher order strategizing, right? Like math isn't just about calculations. It's often about big picture ideas and then doing rough drafts to try to make a strategy work out. And it's often about joy and communication. And so part of what happens then here is that math sometimes happens because of relationships. It often involves a winding journey through many different ideas and putting them together. All right, so those are some of the themes that I hope come out. All right, so let me talk a little bit about privacy by first talking about data. Let's think a little bit about how data is used these days. Often there's lots of data collected about us. Keystrokes, website visits, browser info, how you sleep, right? These are all things that we have multiple devices now that do things that are kind of incredible. This is useful, right? Like I might want to think about my sleep habits and sleep patterns in order to see trends or diagnose certain problems. We use our GPS equipment to navigate. But of course, part of the issue is that even with this usefulness, there's a concern about privacy, right? Often the privacy you think about is your data getting into the wrong hands, right? But I want to say that privacy is actually more than just worrying about security, right? Your data, security is worrying about unauthorized access. Okay, well, actually, authorized access might itself be a problem. Privacy is also more, isn't just about keeping your name off the data. Why? Well, because even people who have access to data, even if your data is anonymized, they might still be able to learn something about you. Okay, so that's a key point I want to make here, that legitimate access to anonymized data might also reveal too much. Okay, so what happens? Some people, maybe you decide to participate in a survey and you give some information to somebody who takes a survey. Okay, so that's, and then somebody else comes along, maybe another researcher, maybe an adversary, somebody comes along and has access to that data, legitimate access to that data, and they ask a question on the data, right? So the question might be, how many people in this data set have a certain disease? Now, you participate in this survey, and this data doesn't have your name on it. It seems like it should be safe, right? Well, maybe this question seems okay. How many have this disease? What about this question? How many Asian males in Oakland with a particular birth date have a particular disease? Can you see why that might be an issue? Yes? Just take a moment, in 10 seconds, talk to your neighbor about why you think that might be a problem. So let's think about this surprising fact. So it's Sweeney in 2000 showed that almost all the population, 87% of the population, can be re-identified just based on 3 things that are often found in lots of data sets: your zip code, your gender, and your date of birth. That's enough to uniquely identify 87% of the population. Okay, well, I didn't put my name. My name's not associated with this data, right? Well, if you just cross-link, for instance, imagine having one database that has zip code, gender, date of birth, and a particular in medical records, and another in voter registration lists. And then by cross-linking the two, you can actually learn somebody's identity. That's a problem. Similarly, your browser actually leaves a digital fingerprint every time you visit a website. That website learns 3 things about you: your browser type, your installed fonts, and your time zone, right? How secure is that in some sense? How much are you revealing about yourself by visiting these websites? That's a question we should be concerned about. And part of what I want you to see here is that new information can make earlier data sets vulnerable, right? Like maybe earlier, maybe you participate in some survey today, and then 20 years from now, you participate in some other survey, and then boom, there's a connection that's possible that wasn't possible before. Or maybe new strategies, new techniques will make your data vulnerable. Okay, so this is what differential privacy is trying to address: legitimate access. How much of your data is being released? And that brings us to the subject of differential privacy, which is pioneered by Cynthia Dwork in 2006. It's the idea that we're going to use often, not every, but often, differential privacy is achieved using randomness. Okay, and I'll explain in a minute how that happens. But I want to just say at a high level, the whole idea here is to be able to quantify how much of your privacy is being released every time somebody asks a question on a database that you've participated in. Are you with me? And so what we'll say is this algorithm asking this question has epsilon differential privacy. It's epsilon differentially private. Okay, so I'll explain what that means later, but that's the idea. And so the idea is by being able to quantify this, it keeps us from having to worry about What is the extra info someone's going to learn? What computational strategies are going to become available to a person? Right? I can say that this is the amount of privacy that's being lost. And not only that, there's lots of great properties of this definition that I'll show you. One of the properties that's wonderful is we can know then if you ask a question of the database and you ask another question of the database, together, how does the privacy loss of those two questions add? Are you with me? And guess what? The surprise is that they actually just add, right? Like if your first question is epsilon1 differentially private and your second question is epsilon2 differentially private, then together, those two questions have differential privacy of epsilon1 plus epsilon2. That's a great property. We can just talk about adding up how much privacy is being lost. Another thing that's great is that processing the data afterwards doesn't change the privacy level. So if you ask a question of the database and someone else uses that information in some way, it is still going to have the same. You're not gonna have any the privacy level is not going to change. Okay, so this thing sort of popped up on the scene in 2006, and I think it was maybe 2008, 2009. I first heard about this, and you can see now today lots of different companies and the U.S. Census Bureau use differential privacy to protect user data. So Apple has a whole website, for instance, on this, where they talk about differential privacy. And I'll just mention here that they say, hey, Apple uses local differential privacy to help protect privacy of user activity over a given time period while still gaining insight. So that's the key. And I'll show you how that happens. That kind of thing happens in a minute. And so they talk about Apple seeking to have a privacy budget. So they keep track of how much privacy is being lost by you in the usage of data. Okay, and they retain this data for a certain maximum time, and they go further to explain this, what they're doing with the data. Okay, so let me give you an example of how you might use randomness. So that's the second thing in the title, to protect privacy. So here's a question. Suppose I am a pollster trying to determine what fraction of you have cheated on your taxes. Now, I know some of you are like, I'm not old enough to file for taxes, but it could be some other question, right? It could be, who did you vote for in the last election? And of course, some of you are like, well, I'm not old enough to vote in the last election. But yes, lots of different questions you could potentially ask where people might be embarrassed to say the true answer. Are you with me? This is a problem with surveys that, people might be shy to say whether they really cheated or whether they really voted for that candidate. So how in the world are we going to, how can we solve this problem? So Warner in 1965 suggested this idea that instead of asking people to answer the question, we're actually going to give them a coin. Okay, I'll give you a coin, and I'll ask you to flip the coin. You flip it, okay? You don't even have to show me the result. You flip it, and if the coin comes up heads, I'd like you to just say yes to the question. Right? Did you cheat on your taxes? Yes. If the coin comes up tails, then you actually answer the question. Did you cheat on your taxes? Are you with me? Does everybody see this? Okay, so now imagine every time I pull every single one of you, I just give you a coin, you flip it, and you do this. If heads, you say yes. If tails, you answer the question. Do you see why that's actually going to be make people a little less shy to answer this question? Yes, they don't actually have to reveal whether they actually cheated on their taxes. They just half the time are going to answer heads no matter what. Are you with me? Okay. Okay. So that's interesting. So here's how randomness is being used to protect privacy. And now let's see how you might still be able to get good answers. So think about this with me. If you have 1,000 people and you got 700 yeses by doing this modified polling strategy, what does that say about the original data? Well, assuming everybody's flipping fair coins, would you agree that about if you got 700 yeses, you actually know about how many yeses you expect to get from just people who got heads? Are you with me? How many do you expect to get? About half of them, 500, yes? So about 200 of them are going to be actual answers to the question. And that's out of 500. So 200 of the other 500 came from answering the question. Then you could conclude reasonably that about 40% of the people cheated. Are you with me? Okay, so you can still get useful aggregate information even though your data has been masked, even from the pollster, right? There's plausible deniability that each person has in answering this question. Now, you can see that, of course, really what you've done is taken this survey on half the people, not the whole set, right? And so there is a loss in accuracy. With 500 people, you're going to have maybe not as good an estimate as with 1,000 people, yes? And so there's a loss of accuracy that comes with this trade-off. But you can see here from Apple, again, that what did they do? So they're talking about injecting noise. So noise is the statistician's way of talking about injecting a small random number in there and adding it or doing something. Here, in this case, what they do is they take the coordinate of a vector of whatever it is data that they're looking at, and they flip coordinates with a certain probability, one way or the other. Okay. And that's where epsilon is a privacy parameter. Okay, so by doing this flip, they're saying that this part is contributing epsilon to privacy loss with an epsilon differential private algorithm. Okay, and it's just like what you said. The whole idea of local differential privacy is the person's data as it comes in, the inputs are actually being randomized then. Okay, so Apple actually doesn't keep track or doesn't know the true values beyond that point. Okay. All right. Good. So what's the message? Randomness provides some privacy. There's a trade-off between privacy and accuracy, and randomized response is one example of a randomized algorithm. So I have to now say, what is a randomized algorithm? So a randomized algorithm, one way to think about it is it's a procedure that you perform on whatever it is, some data, and it's randomized because each time you perform it, even on the same data, it might produce a different answer because of some randomness there, right? So, so that's what more formally, what is it? It's an algorithm M takes some data set X, and here X is like a whole list of how people voted, every voter, yes? And it outputs something which might be an estimate of how popular the candidate is. And that's a random variable. So if you don't know what a random variable is, just think of it as an output that has some randomness in it. Okay, the answer won't be the same every time you run the algorithm. Okay, randomized response is an example of that. And so we'll talk about a randomized algorithm as being epsilon differentially private, as being a statement about the privacy loss. Okay, so the next slide is the only technical slide in this talk. Okay. And so don't be scared of all the symbols. But the idea of differential privacy is the idea that you want it to be the case that no one person's data has much influence on the outcome of a question you could ask of the data. Are you with me? So that's the idea. And this mathematical formalism, this inequality is trying to capture that. So we can say two data sets are adjacent if they differ in just one person's data. Okay, so if I poll all of you, asked who you voted for in the last election, that's a data set. If I poll all of you and ask who you voted for in the last election and one of you flipped, that's an adjacent data set. Are you with me? Okay. And now a question I could ask of the data is, what fraction of you voted for Trump in the last election? Right, there's a question. Yes. And if I got that answer and for one data set and I got it for another data set, then compared them, could I learn something about how a person voted? And the answer is here. Well, it doesn't. That actually, I could see if I know this data differs from this one for this one person, and they flipped, that suddenly changed the numbers a little bit. Yes. Okay, so that's we want to think about algorithms using randomness that won't have much effect. And so what does this this equation inequality say? It says if you have the output m of x of some algorithm, the probability that that outcome is in a certain set of values is not much different from the probability when you do the algorithm on an adjacent data set. That's all it's saying. How different? By some small some factor that's just slightly above, it could be 1.01, right? That'd be a 1% difference between these two probabilities. Are you with me? Something like that. Yes.
Should be a set of real numbers separated by m or more general?
It doesn't have to be real. It could be more general. It could be a vector. It could be anything. Yeah, if I were saying this in probability language, I would talk about events. Probability that m of x lands and is in some event. Okay, good. So that's the definition. And I'm just going to point out that this isn't actually the definition. This is probably the easy way to digest the definition. But in practice, the definition uses a factor epsilon, e to the epsilon. Now, you might wonder, why in the world would you do that? But you might know if you've taken high school calculus that e to the epsilon, e to a very small number, is actually very close to 1. How close? It's about 1 plus epsilon. Are you with me? Okay. That's a property of e that's being exploited here. And why would you do this? Well, it turns out that the additive, so what happens if I take e to a number a times e to the number b? What is that, everybody? E to the a times e to the b, it's e to the a plus b. So the exponents add when you multiply these things. Are you with me? That actually helps us get to this thing where if you ask a question twice, the privacy losses add. Okay, so this is one of the reasons that we use the epsilon. All right, that was the most technical bit. So let me show you another randomized algorithm. So suppose you have a data set that includes how all of you did on the last exam you took at proof school. Okay. And maybe that average score is 78. Yes? Now, as I alluded to earlier, this is actually not differentially private. Why? Well, if, for instance, tell me your name. Garrett. If everybody at proof school took this exam on one day and the average was 78, and Derek happened to be absent that day. Okay, so somebody asked a question, how did we do on the exam? And the teacher says the average was 78. Okay, then Derek comes back from his illness and then takes the exam. And suppose somebody asks the same question a few days later. What was the average on the exam again? Oh, it's now 76. Oh. We just learned something about how Derek did. Do you agree? Okay. Okay. Not good. Okay. But so here's what we're gonna do. We're gonna solve this problem by adding a little noise to the answer. Okay. So I'm the teacher now, and people ask me, how did everyone do? What's the average on the last exam? I won't answer 78. I'll just answer 78 plus a little random number. Are you with me? Okay. Every time somebody asks me the question. So they could ask it several times in a row. I'm just going to answer 78 plus or minus a little number. Are you with me? Okay. That's how I'm going to solve the problem of privacy. So that when Derek comes back from his illness, no matter how he does on the next exam, do you agree that if I answered 78.1 one day and 77.2 another day, people aren't necessarily going to associate that with Derek? Yes? Do you agree? That's privacy. That's epsilon differential privacy if you do it right. So how do you do it right? Well, you add a little bit of random noise, and the random noise you're used to thinking of is a bell curve shaped distribution of noise. But it turns out if you use this other distribution called the Laplace distribution, which looks kind of spiky, then has lots of nice mathematical properties. In particular, privacy losses behave in very simple ways. That's the thing to think about. Okay, so this is called the Laplace mechanism for randomizing an answer to a question. Are you with me? Okay, there's many other kinds of ways to do differential privacy. This is one of the first basic ways to think about it. Now let me see, bring you to my next point, which is this idea that randomness is good, it's being used in some way, but it's also costly. It costs us something. Okay, so I'll just point out that that large-scale deployments of differential privacy actually require a massive amount of high-quality pseudo-random bits. Okay. In fact, the U.S. Census Bureau in 2020, it's estimated, needed at least 90 terabytes of zeros and ones. Okay. And just to give you some idea of how big that is, Library of Congress would fit on in 10 terabytes. Okay. So we basically need to come up with a way of generating random zeros and ones, 90, I'm not sure how many billion. Anyways, we need 90 terabytes worth. Are you with me?
9 libraries.
9 libraries of Congress worth. It's hard to do that with efficiency and security. Okay. And I'll just leave it at that. All right, good. So this is the research question, and the idea that Salil and Clement was studying when I met them was this idea that, like, oh, well, we should try to quantify this. What's the minimum amount of randomness you need in order to still have accurate answers? And that's, for computer scientists, they often think about measuring the costliness of things, like how much time does this algorithm take? That's called the complexity of the algorithm, right? Here, randomness complexity is how much randomness do you need to get accurate epsilon differentially private releases. And so we initiated this study of randomness complexity by studying a particular example I'll show you in a minute. But the definition here then is randomness complexity of an algorithm is a certain measure of the expected number of coin flips I need in order to run the algorithm. Are you with me? That's the way to think about it. A useful fact is that the expected number of coin flips is actually related to another quantity. Here's another connection being made to this idea of entropy, which is, you might have heard this term. How many people have heard the term entropy used in some contexts, usually in physics, okay? But is actually also an idea in mathematics. So the idea of entropy is this idea of quantifying the uncertainty in the amount of information you know, okay? So in physics, you often think about low entropy configurations and high entropy configurations. It's actually related to this idea. A high entropy configuration is one that you have more uncertainty in knowing what the state of the system is. And there's this formula, which some of you may have seen in some contexts, but let me just say this. Entropy, one way to think about entropy of information is how many yes/no questions does it take to determine the value of a random output? Okay, so a random, whatever the random output is, every time I run this algorithm, I'll get a different number. Okay, and so now the question is, how many, if I'm going to be judicious about the questions, how many yes/no questions do I need? So I think about the game 20 questions. How many people have played that game? 20 questions to try to figure out some characteristic about something somebody's thinking, yes? How do you play that game in an optimal way? Well, the optimal way is you try to ask a question that's going to cut down the answers in half each time. That's the best way. Would you agree? So that is actually just like asking how many times you need to generate, how many 0-1 bits you need to generate a random outputs answer. So let me see if I can explain why. So the best question tree, you have this tree of possibilities. You're narrowing it each time. If they answer yes, I'll go down this part of the chain and ask a different yes/no question. If they answer no, I'll ask a different yes/no question. Yes? Agreed? Okay. So the best question tree always divides the possibilities in half. And so if you want to actually run an algorithm that is going to produce a certain output, some output, you could just run this question tree each time using a coin flip. because you want them to be 50-50. And so if you go down this tree in exactly the same way, and then at the end of that tree, you just output the value that's supposed to be the result, that is actually going to generate this random variable. Okay, that's the only idea you need to know about entropy. If you actually calculate the expected optimal ways of doing this question thing, you're going to get an expression like P log P. Okay, so third part of my talk is geometry. Okay, so where did that enter in? The idea of geometry. So we decided that it would be useful to just look at a particular common kind of example where we can try to answer the question of what the randomness complexity is. What's the minimum amount of randomness needed? So here's a typical question. Maybe I'm Apple and I'm collecting information about the popularity of certain emojis. Okay? So each of you actually is a row in this matrix. Okay? The first row is keeping track of which emojis Derek uses. Okay? The second row is keeping track of which emojis Eugenia? Medina uses. Yes? Each row, each of you has a row in this matrix. Are you with me? Okay. So this is, you can think of this data set, this whole thing X is just a big matrix with n people keeping track of D attributes. Okay? And to talk about popularity, I could just go down and sum how many times each of these particular emojis are used. Yes? Okay. And so here I can see by looking at the column sums that, that the second emoji, the heart, is used the most. Are you with me? Everyone see how I'm getting this information? This is the input. This is the output. It's not random. Okay? As soon as one person leaves this data set, this answer is going to change in a way that if I knew, I could unpack what the other person's information. So what do you want to do? You want to design an algorithm that's epsilon differentially private, that's still accurate, and is still close to this number. So let's do a version of adding noise. So I'm going to add a little noise. And so this sum is now going to be this sum. Okay. And one problem, of course, when you do this is that adding noise is actually a high entropy thing, okay? Because you're increasing the different kinds of possibilities that are there. And so we have to actually solve that problem. So here's the idea. It doesn't quite work, so we just got to modify a little bit. So this is our idea. We're going to basically take every point to a nearby point by rounding. So for instance, if this is my true value and I hop over to a green point here, which is my noise, some item in the noise cloud here, what I'm going to do is if I land in this square, I'm going to move to the center of the square that it's in. Okay. So that's a certain rounding. And so here is where geometry starts to take shape. Because here we now have a problem we're thinking about as a geometric problem. And one of the questions you might ask then is, well, how do I round? Like, I don't want it to just do anything. I want it to do this in an efficient way. So what I've just suggested here is one where a very typical way of rounding is just to divide things up into a grid and send points to nearby points, okay? The problem is that this is a kind of still a lot of possibilities, okay? For instance, whenever you have a true value and you hop out a little bit, it could hop into a number, in this case, 4 different boxes potentially, okay? And that may not seem like very bad at all, but if you have high dimensional data, I'm keeping track of 100 emojis, then in fact, that's 2 to the 100 different nearby points. That's bad. That's high entropy. Are you with me? High entropy means high randomness complexity. And so a question you could ask is, can we do better than this? Like maybe this rounding scheme is not actually a good one. Okay, so here's where, at this point, is the point at which I came into the picture, because I said, you know, Sperner's lemma actually might be able to solve this problem. And it turned out we had a bunch of proofs that related actually very closely to Sperner's lemma. And then we came across the work of this group of computer scientists, van der Waal, who actually had something they call deterministic rounding scheme. And by actually appealing to their work, we actually came up with simpler and better proofs than the ones we had. So Sperder's lemma never even entered the picture anymore. But let me show you what their rounding scheme did. So they weren't thinking about this in the context of differential privacy because they call it deterministic rounding. They're doing something else with it. But the idea here is if I take the standard grid and I just shift the boxes a little bit, do you see that for a two-dimensional grid, you now have a situation where if you move into a neighboring region, you only hit 3 boxes rather than 4, yes? Okay, but the key thing is that in higher dimensions, you can even do much better. So here's what you might imagine doing. If you took the standard grid in 2 dimensions and you shift it a little by, I think it's a half each time, you get this shifted grid, yes? And now in the 3rd dimension, if you take those shifted things and then you shift each of those in 2 directions by 1/3, then you get a picture like this. And if you keep going in every dimension doing the similar shifting, what you end up getting is a set of boxes that are, if you add a little noise, only sent to, guess what, D plus 1 nearby points. So if you're keeping track of 1,000 emojis, it's not 2 to the 1,000 boxes that different points you're getting sent to. You're only getting sent to 1,001, which is really good from a computational perspective. Okay, so the ultimate picture, this is just a picture then of the strategy, is what do you have? You have emojis. You've got some sum that you want. And what you do is you add some Laplace noise. So remember, Laplace noise in 1 dimension is kind of spiky. In 2 dimensions, it looks kind of like a diamond. This is a cloud of Laplace dots around this true answer. And that cloud of Laplace dots kind of has this kind of diamondly shape. So what do? You use this noise, you pick a random Laplace thing, and then you move to the triangular point. That's the answer plus noise. Okay, the problem is that has to try to control the entropy. This is a technical point which I won't dwell on here. You snap to a grid, a small grid here that's got those are the black dots, and then use that point, which is now some object, and then you use the rounding scheme to move to the center of some box. Okay, and so here, this particular, if you control the noise here, then you only ever end, with high probability, only ever end in 3 boxes. Okay, and that is a low entropy randomized algorithm. Are you with me? And there's a theorem from information theory which basically uses the 20 questions procedure. It's called Huffman coding, that says whenever you have a random variable that outputs a discrete random variable, it can be there is a way to generate it using basically an entropy number of questions. Okay, and that's a number of random bits. So this is the results that we had, which is basically that for accurate differentially private summation in D dimensions, that's keeping track of D emojis, what we had guessed before we did this work was you'd probably need D random bits to do it. But it turns out to be much smaller. It's actually log of D random bits. So if you had a large number of emojis you're keeping track of, this is actually a small number of random bits, right? 1,000 is a lot bigger than log of 1,000 random bits. And so this is only the first of a number of questions you could ask. I know that part of the idea of the Ross lectures was to introduce high school students to active areas of research. Okay, well, here's some lots of questions that are generated. One is, are there other kinds of queries you could analyze to try to understand how many random bits are needed to generate accurate answers. Another thing that's open is this question of how you get efficient low random mechanisms. So this procedure that we talked about, at the very end, I kind of said, hey, we appeal to a theorem. And the theorem says that you can always generate a discrete random variable using an entropy number of bits, right? Well, how do you actually get from a, how do we actually do that? That uses this idea of 20 questions Huffman coding. But that procedure actually is hard to make work in practice. And so are there ways to do that? Okay, anyways, if you're interested, there's the QR code actually can give you a little bit more details, maybe more than you want to know, the actual paper. And I'll just finish then by reminding us what you've hopefully taken away a little bit from this talk, like the idea that math is often about this journey of trying to put together pieces of things in ways that will help. You have to strategize, right? In ways that'll help answer the question you're interested in. It's about figuring out how to communicate the ideas that you have in ways that actually make sense, right? And it's about relationships. I had a lot of fun reuniting with my former student and learning something from him. So in some ways, this was a full circle journey where Salil became my teacher. Thank you very much. Thanks for being here.